All right, good morning, everyone. Hope you guys had a nice weekend. Let me start off by just going over the calendar for this week. So last Thursday, we started quiz review worksheet 1. I think we got through all the first page. We started the second page, but we ran out of time, so we're going to finish that worksheet today. There was also homework number 7 that was assigned to you from last Thursday. So Friday was asynchronous day. I recorded a bunch of videos going over the homework assignments. So you guys can find that under Friday's link. Today, we're going to finish up worksheet 1, and then we're going to start worksheet 2. Okay. And you guys also picked up homework number 8. And tomorrow is asynchronous day. Only the juniors will be here at school. There's no new assignments. There's no classes tomorrow. But I'm going to ask that you guys turn in your homework, your AP assignments 5 through 7 by tomorrow night. So that is the homework that was assigned Tuesday, Wednesday, and Thursday of last week. So notes and homework number 5, notes 5B and homework number 6, quiz review worksheet 1, which we'll finish today, as well as homework 7. Okay, so that is due by tomorrow night, midnight. Again, if you don't turn in by tomorrow night, you can still earn an A on it, so it's not going to hurt your grade if you turn in. It's not going to hurt your grade terribly if you turn in late. But I did want us to get this in by tomorrow, so that you guys have those additional or these assignments finished, so I know that you guys are working towards preparing for the quiz, which is on Thursday. All right. Wednesday, we're going to start up. We're going to do worksheet number 3, and there's homework assigned Wednesday as well. So the homework that you just picked up and the notes that you just picked up for today, that and Wednesdays is going to account for the 3rd assignment. Initially, it was going to be due Friday, but I'm just going to push it out to Sunday, just give you guys more and more time to complete it and submit it. So this is going to be the last assignment that's going to form your first quiz grade. Right? So your first quiz grade is made up of assignments 1 through 4, 5 through 7, and 8 and 9. So all that's going to total to be 100-point quiz grade. But I'll put it in teams under 3 separate assignments, but it really is just going to combine to be 1 quiz grade. Okay. The quiz that is on Thursday is going to be very similar to the topic that's covered on worksheet 1. Okay. So we're going to do we'll finish worksheet 1. We'll do worksheet 2, we'll do worksheet 3 today and Wednesday, but it's all going to be circling around the same topics, okay? And your quiz is going to be like this. It's going to have 7 parts, okay? So it'll be front and back. So, okay. We'll finish the rest of it today, but just to let you know what your quiz is going to be like, it's going to be very much formatted like review worksheet 1. Okay. Now I'll give you a table, I'll give you a graph, I may give you a function, and I'm going to ask you a variety of questions. Okay. You guys also picked up a formula sheet, and the formula sheet I included if you're on Teams under today's link. So this is the FRQ quiz formula sheet. I will include this. I will attach this to your quiz on Thursday. But I also want to just kind of show you, what we're going to eventually work towards memorizing, okay, for the AP exam. I know this looks like a lot, but I think that you probably already are pretty familiar with at least half of this, right? And so over the course of this next month, we're just going to continue to go over these or apply these rules, right? So I think within the next month, you're going to see this on a daily basis. And so by the time it gets to the time where you have to memorize it for the AP exam, I don't think that's going to be a big jump, right? Because you're seeing this every day, and you already have half of this probably committed to memory in some form or another. So now I will say that this is not 100% of what you need to know, but I would say this is probably like 85%. Okay, I left off some things from limits like continuity conditions. Okay, so we'll review over that, but it's not going to be on this quiz. And also I left off area volume from chapter 7, right? Disk method, washer method, cross section. But I think you kind of know. I think you know that already. It's just circle formula with integral in front of it. So I'll, as we get closer towards the exam, I'll try to make a compact formula sheet, probably a page and a half, so that you can just focus on memorizing those heading into the AP exam. Now, it's possible that some of the more obscure rules can come up, but I don't see it very often. In the last 5-10 years, I just haven't seen a lot of obscure rules come up. But if you want to be sure, I'll also provide you the full derivative and integral formula sheet if you want to just to commit those to memory as well. But I want to at least provide you with, here's the bare minimum, right? If you can know this, chances are you have everything that's covered on the AP exam. Okay. Okay. Any questions about this week? I'm going to have some help sessions over the course of this week as well. So tomorrow afternoon, I'll do a help session going over homework 8. Wednesday afternoon, I'll have a help session going over homework 9. And then Thursday morning, I'll have a help session for your AP quiz. So, and I'll record each of those sessions as well. Okay. Yeah, and I'll send out a remind tonight for reminding you about your assignment 5 through 7 due tomorrow midnight. Okay. Okay, let's go to worksheet 1 from Thursday. Let's do a recap of what we covered from last Thursday. We talked about how if we want to guarantee a specific second derivative value, we can go through mean value theorem. Because if we can guarantee that a slope of f prime is going to give us -3/4, then we know that there must be a slope on the f prime graph, which is f double prime, must be equal to -3/4. And we're able to prove that the endpoints of the f prime graph did give us a slope of -3/4. So we know there must be an exact slope value that lives somewhere along that f prime curve. Okay. Part B. We talked about how we can write the equation of a tangent line by gathering order pair and slope. But to get our order pair, we just insert into our composite function. But to find the derivative, because we have a composition function within the function, we have to go through chain rule, right? So having to go through chain rule, then inserting our order pair into chain rule to get or into our composite function to get our slope, and then putting it into point slope form. Part C, finding slope again, but now these are explicit functions that we have to go through chain rule for. So we had to go through cosine u times u prime, e to the u times u prime, cosine of u's derivative, insert our x value of pi into the derivative, And then whatever value we get at the end must be the slope value at that point. For D, we talked about how to find H and H prime, we have to understand that there's that relationship between H and J. And here, we see that relationship here, which tells us that J is sitting at a level below H, because it takes an integral of J to move that J function to be at the same level as H, which is really telling us that J is sitting at the H prime level. So that's the relationship. Okay, so to find H of 4, we just follow the rule, and we know that we're just going to accumulate that triangle, area of the triangle to get the H of 4. But to find H prime is really our J graph. So we just have to look for the order pair. So H prime of 4 equals 0. Okay, second page. We talked about how because our J graph is our H prime, that we were able to label our derivative graph and gather information about the derivative graph, looking for x-intercepts and looking to see where our graph is above and below the x-axis. So wherever the graph is above the x-axis, we know that's going to indicate where our original graph is rising. Below the x-axis means where our graph is falling. Okay. And then we also wanted to create a second derivative sign line, because we're asking to see when does the graph have both of these properties existing at the same time, where the graph is both rising with an up arrow and concave down. So we need to create a second derivative sign line as well. To do that, we pick out our points of inflection. Our points of inflection on the F prime graph is going to be where the peaks and valleys are, where the relative max and mins are. So we know there's a POI at 1, POI at 3, POI at 5, and then we look at our slope, right? Whatever the slope of our derivative graph is, it's going to translate to the concavity of the original graph. So this portion is going to represent concave up, concave down, concave up, concave down. So now that we had our sign lines all lined up, we're just looking to see where those two symbols are going to match up. So between 1 and 1.5, we see there's that overlap between positive slope and concave down. So we want to include that between 1 and 1.5. And then concave down between 5 and 6, because we see both behaviors occurring at the same time. Okay. And the reasoning is because H prime is greater than 0, H double prime is less than 0. Okay. Any questions so far? Okay, that brings us to F, and F is asking for find the absolute min and absolute max. Okay. What does that remind you? We got to apply what? To find absolute max, absolute min. What theorem is involved here? Rolls is if we're trying to guarantee a slope of 0. Yeah, this is extreme value theorem. Okay, so F is extreme value theorem, EVT. Now, I do want to point something out here is sometimes you may see on the free response or AP exam where they leave out the word absolute and they just say find the minimum value, find the maximum value. It's implied that it's absolute. Okay, so just be aware of that. If they say find the minimum value on the closed interval, it's understood that they're asking you for absolute max, absolute min. Okay. So we want to find absolute max, absolute min of h of x on the closed interval from 0 to 6. So as a reminder, we have a couple of things we're looking for, right? EVT, we want to look for candidates for max and min. So candidates are going to be endpoints. So we want to consider endpoints or test endpoints. And then we also want to test critical points. So endpoints are at x equals 0 and x equals 6. And then critical points are at the relative max, relative min, right? So 1.5 and 4. Okay, we don't want to involve 1, 3, and 5 because 1, 3, and 5, these are points of inflection, right? And we know that points of inflection, right, has no chance of being a max or min, right? It's the transition point from one concavity to the next, so it's not going to make sense looking at those values for to determine absolute max or absolute min. Okay, so we're going to test our endpoints and our critical points. We're going to find the max and mins of h. And if we look, we have our h of x defined here. So we're simply going to plug in one at a time. We'll find h of 0 first. So I'm just going to follow what the rule says. Oh, and by the way, yeah, these variables should be presented with different variables in my upper bound. So j of t dt. Okay, so h of 0 is the integral from 6 to, so I'm just going to replace wherever my x is. In this case, my x is sitting in the upper bound location. And we have the j graph here, so we're basically just going to be accumulating the areas that we see there, right? So we see a bunch of triangles, so a bunch of 1/2 base times height. But is there an adjustment that we should make before we go to the graph? Yeah, let's flip the bounds. Now, you don't have to, but I think it just makes things consistent, right? If we always flip the bounds, assuming that we want to read the graph, we can just always read the graph from left to right, rather than having to adapt. Oh wait, do I need to go backwards? So if we make that adjustment here, then we can always read the graph from left to right. Now, if this is a problem where you're just trying to find the integral of like x squared, and you're just going through power rule or integral rule, then you can just plug in the bounds with whatever order they give you. I mean, you can flip it, but it's not as important. But I think reading your graph, I think it's nice to always read from left to right rather than having to read from right to left and to change the signs in our head. So I'm just going to adjust, flip the bounds, make that adjustment. There's a negative that sits outside. And now we can just read the graph as we see it, right? Above is positive, below is negative, and then this negative out front will change that after we accumulate what we see in our graph. Okay. So all of these areas here, I'm going to highlight these triangles. One-half base times height. Okay, so my base here is 1.5. Height is 1. So 3/2 times 1/2 is 3/4, which is 0.75. The second region, we see a larger triangle, but it's below the x-axis, so we know it's going to have to be negative. The base is this distance here, so if I count, that's 1, 2, 2.5, right? 2.5. My height is just 3. So if I multiply that together, 5/2 times -1/2 times 3, it's just going to be negative 3.75. Finally, we have a triangle that's above the x-axis, so 1/2 base times height. So that's just 3. Right, so I think we have enough to start gathering information. We want to look at the accumulation of those regions from 0 to 6. So we have the 0.75. let me push a negative out here in front. Positive 0.75 minus 3.75 plus 3. 0.75, negative 3.75 becomes negative 3. Negative 3 plus 3 is 0. Negative 0 is just 0. Okay, so 1 down, 3 more to go. Let's find h of 1.5. Again, we're following the rule here. The rule is inserting the x value into the upper bound location. Again, the bounds are out of order. I'm going to flip the bounds and change the sign. But now we only have to accumulate the triangles from 1.5 to 6. So it's just going to be these two. So negative 3.75 plus 3. Okay, so the result of this is going to be negative 0.75 with another negative in front. So 2 negatives gives me a positive. Next up, h of 4. Again, out of order. For 6, it's just that last triangle here, so positive 3. Finally, h of 6. H of 6 will be the easiest because the bounds are the same. And if the bounds are the same, we know that there's no area that is being accumulated, so it should always be 0. Okay, we've gathered all the information that we need to make our conclusion. Any questions so far? So what would you say is the absolute max value? Okay, and what's the absolute minimum value? Negative 3. Okay, it seems straightforward, and it is, but I want to just kind of talk about the fact that when it's asking for absolute max and absolute min value, it's just the y value that we care to give. Okay, so if you give it as an ordered pair, then it's not perfectly correct, right? Because we can't give the same emphasis for the t value and for the height or the y value. So either you write it without even mentioning the t values, or if you want to mention it with the t values, you have to make sure that it's de-emphasized. Right? So either you just say absolute max is 0.75, absolute min value is negative 3, and then just be done with it, and that's perfectly fine. That's acceptable. Okay, that's what I prefer. But if you really want to include the x value, you can put it off to the side and say, okay, it should have this be at x equals 1.5. Okay. But if you say that my absolute value is parentheses 1.5 comma 0.75, then you'll get partial credit, but it's not fully correct. Okay. So the answer is at the y value, not the x. Even though they feel like, they are equivalent in importance. Yes. Oh, that's right. You're right. Yeah, this should be t. Well, let's see. Yeah, sorry. J is in terms of t, but then once it gets pushed in, it's going to be in terms of x. Yeah, so it should be x. Yeah.
Is your
Exactly right. On the AP exam, they don't have to. They're not requiring you to say by EVT, absolute max is this, absolute min, and give all the reasoning. Yeah, that's good. That's a good point. The work that you show just by testing your endpoints and critical points, AP exam is going to count that as justification. That is showing that you are going through the full process of EVT. You don't even have to mention EVT, but the work shown is your justification. Okay, any question with F? Okay, let's look at the last part of worksheet 1, and that is asking to evaluate the definite integral from 1 to 3 of f double prime of 2x. Okay, there's two things that I want to point out with this process. The first is that there's something about that 2x that we got to keep track of, right? It's not the same thing as the definite integral of f double prime of x. That 2x, we know there's something extra going on there. But we don't do chain rule, right? Chain rule is for derivatives. The equivalent or the integral version of chain rule is called U substitution. So we have to go through U substitution. And the point of U substitution is to allow us to keep track of what's going to happen with that internal 2x. The second thing is to understand that there's an integral process going on here. So this is an application of first theorem of calculus, FFTC. So I want to ask you this here. If I want to ask you for the definite integral from a to b of f double prime of x, what's going to happen to f double prime if I push it through its antiderivative?
Just f prime.
Good, just f prime. And then once you're at f prime, you can work in your bounds. All right. So I think we're really comfortable with derivatives, right? We know f becomes f prime because f double prime, but the antiderivative, we also just have to understand that we're just going back where we came from. So the antiderivative of f double prime is going to move us up to f prime, right? The integral of f prime is going to move us up to f of x. Right. So if you look on your formula sheet, it's just a variation of that, right? If you want to write that in, you can, right? F of x becomes uppercase f. You can say f prime equals f. You can say f double prime equals f prime. It's all that same process. We're just pushing an expression up a level once it gets thrown into that integral process. All right, so I want to keep those two things in mind as we approach this problem. So first things first, we want to get that 2x resolved. We want to figure out, okay, there's something that we got to keep track of with that 2x. So we'll go through U substitution. We'll let the U value be 2x, and we always want to target dx, right? We always want to find a way to get that replaced. Our goal is to get everything in terms of U so that we can see what's the cleaner version of it, and if there's any coefficients we got to keep track of. Okay, we'll let the U value be 2x. Remember, our U value is always going to be, well, at least with these problems, it's easier to find. It's just whatever is inside the set of parentheses. Okay, du dx equals 2. Cross multiply. We solve for dx. Okay, we make our substitutions. Now, when you make your substitutions, don't plug in the bounds yet. Okay, so we'll deal with the bounds later. Everything's in terms of U, nothing to cancel out, but we need to keep track of what? That 1/2. Okay, so I'll push that 1/2 out in front. Okay, let's go ahead and apply the antiderivative, right? We know f double prime is just going to turn itself into f prime. We'll keep that 1/2, so 1/2 f prime of u, and then we got to worry about the bounds, right? this is where we got to plug in the upper and lower bound. But at this point, can I use 1 and 3 with this expression?
No, it's not.
Okay, they're not the same variable. So there's two methods, right? Either you get everything in terms of u, or you get everything in terms of x. But you can't plug in the x into the u because that's a mismatch, right? So let me go through two methods here. And you can choose whichever method you want to use. Here's method 1. So method 1 is where I'm going to I'm going to convert the bounds. So if x, my old lower bound was x equals 1, after I push it through the conversion is always going to be your assignment between your u and x. So whatever you assign your u value to, that's going to be how you're going to convert from one variable to the next. U equals 2x. We insert 1 in for x. So 2 times 1, which is 2. Oops. Okay. My old upper bound was 3. U is equal to 2x. Push that through. 2 times 3 equals 6. So now it's suitable. Now we can use our adjusted bounds. Our bounds are in terms of u. Our antiderivative is in terms of u. So now we can plug in. 6 goes in first. Okay. We have a table of values at the top of our page. So we're going to look at the table of values and see if we can replace them with replace these notations with actual values. So we go to the top. F prime of 6 is 2. F prime of 2 is 3. One minus 1.5 is just negative 0.5 or negative 1/2. All right, so that's method 1. Okay. The other method is where we get everything in terms of x. So after you find your antiderivative, this 1/2 f prime of u, you're going to bring it down, or not bring it down, you're just going to change that to be in terms of x. So replace the u in terms of x. So 1/2 f prime of 2x. And then you can use the original bounds. Because my antiderivatives in terms of x, my bounds are already in terms of x. These variables are matching. Upper bound first. 3 times 2 is 6. 1 times 2 is 2. I'm sorry. Yeah, f prime of 6 minus 1/2 f prime of 2. Okay. Okay, same result. Okay, so either method is fine. We just don't want to be plugging in the 1 and 3 into the f prime of u. Okay, then we won't get the right answer. Okay, any questions? Okay, let's see if we can get started with worksheet 2. So worksheet 2, you guys just pick that up. Okay, let's read this problem here. It says a sand pit is being filled with sand whose height at any given time, at any time t is given by a differentiable function, h of t, with domain between 0 and 12 minutes. Let h prime be a differentiable function. So again, differentiable function just means a smooth curve, no sharp turns, representing the height at which the sandpit grows in inches per minute. So h prime is a rate, inches per minute. It is known that h prime is increasing over the entire domain, so maybe that could be helpful for a future portion. Values of h prime are given at select values of t in the table. The height of the sand pile is 40 inches at 9 minutes, so we know that h of 9 is equal to 40. Okay. All right, let's look at part A. Estimate h double prime of 2. With units, explain the meaning of h double prime of 2 in the context of this problem. So h double prime, we have h prime, we want to get to h double prime. So what's that process going to be? What's the relationship between h prime and h double prime?
It's just the slope of h prime.
Yep.
H double prime.
Right. So normally when we see the notation, we think derivatives, right? Derivative is just another word for slope. So really, we just want to understand that the relationship here is that h double prime of t is basically just the rate of change. Or in other words, slope of h prime. Okay. If we had a function, we can find the derivative and we can find the exact rate of change at that moment in time. But here we're given a table of values. The best we can do is to do approximation. So we're just going to find the slope between 2 points. Okay. And our accuracy is only going to be up to a certain extent because it says estimate. So we know we don't have to be responsible for finding the exact value, the exact steepness, because our information is kind of limited. So we'll say h double prime of 2 is roughly equivalent to, I can use that squiggly equal sign to indicate it's an approximation, it's not exact. But we want to find the slope between 2 points. So does it matter which 2 points we choose? Can we just choose any 2 points?
They have to be like outside of, or they have to be like surrounding.
Okay. Yeah. So what would you choose?
I would choose 0, 1, and 3, 5.
0, 1, and okay. You know what? I think that I would do that. Okay, I would do that if my order pair was at 2. If I was trying to find the rate of change and the order pair was given, then I have a couple of options, right? I can either choose 0, 2, 2, 3, or I can choose the average between those two. But I think in this case, we have a very distinct set of order pairs that's better than all the others. And because 2 lands between 1 and 3, I think just using 1 and 3 is going to be sufficient. Right? And I think adding on to what you were saying, we do want to pick points that are immediately surrounding 2 because it gives potentially a more accurate reading. Right? The closer we are to our source, the less time it has to change, drastically. But if we choose, let's say, 0 and 12, it is an approximation, but we have better options in front of us than just choosing between 0 and 12. So we'll say h prime of 3 minus h prime of 1 over 3 minus 1, right? The change in h prime over the change in time is going to give us information about the rate of change, which is h double prime. Okay. We plug in values here. 5 minus 2 over 3 minus 1. And what's our unit going to be? Units of measure.
Inches per minute squared.
Okay, inches per minute squared. Right. We're starting with inches per minute, but then we're finding the rate of that, so it's inches per minute, so inches per minute squared. It's like starting with velocity and asking you to find this rate of change, right? If it's meters per second, you know acceleration is meters per second or meters per second squared. We're just doing that same process here, right? Anytime you're taking a derivative or integral process, your units will have to change, right? You're doing something to the value. Now, what does that 3/2 inches per minute squared mean? What does it mean in the context of this problem? What information does that tell us?
I guess like the acceleration of the sand.
Right. Well, yeah. But the thing is, we want to put it in a way that that's more. I see what you're doing, but can you phrase it a different way?
How fast the rate of change of sand is occurring.
Yeah. Right. So the distinction that's important here is that we can't just say the height of the sand pile is increasing at 3/2 inches per minute squared, right? That's not an accurate description. If it was 3/2 inches per minute, that would be perfect, but it's inches per minute squared, so it's talking about the rate of change of the sand pile. So we can say that the rate of change of the sand pile height, or height of the sand pile, is increasing. Right? It's not the height that's increasing, it's the rate that's increasing. Right? And that's that subtle but important distinction that AP exams love to ask. But the good thing is, you know, there's only so many different ways that they're asking questions, and so by the time we get to the AP exam, we're going to have a pretty good feel for how they're going to ask questions and you know, the repetition of, there's only a certain number of ways they can ask this, right? So, okay, so rate of change of sand pile is increasing at 3/2 inches per minute squared when t equals 2. Okay, any questions there? Okay, let's do one more. Okay, let's do part B and then we'll be done for today. Okay, part B says use a right Riemann sum with subintervals given in the table to approximate the definite integral from 0 to 12 of h prime of t dt. Okay. Explain the meaning of the definite integral from 0 to 12 of h prime of t in the context of this problem. Okay, so I'm going to move this up so we can see the table next to this problem here. So we want to approximate the definite integral from 0 to 12 of h prime using a right Riemann sum. So we're just going to separate this into subintervals, right? And then do width times height for each of our rectangles. So make your bracket go from center to center from center of one order pair to the center of the next order pair. We subtract the t values to get our width. So 1 minus 0 is 1, 3 minus 1 is 2, 9 minus 3 is 6, 12 minus 9 is 3. Okay. Width times height all the way down. And then we'll put a squiggly line again, because it's an approximation, right? We don't know the exact, we're using rectangles, right? We're using approximation here. Okay, and then within each subinterval, I'm picking the height that sits on the right side of each subinterval, right? So 2, and then between 2 and 5, I choose 5. Between 5 and 7, I choose 7. The last interval, I choose 10. Okay, we total all this up in our calculator. It's going to come out to be 84. But what's more important is, what does that represent? What's that telling us? What's the units here?
Just be like the total amount of sand.
Okay, but first, okay, let's get to that. But first, what's the units going to be? Okay, we're starting off with h prime, which is inches per minute, just inches, right? So when you take the integral, you're going to do something with the units, right? You're going to lose a rate. You're going to lose a rate because you're accumulating that rate, so it's going to change into something else. Okay, so 84 inches. Now, this is something I want to talk about here. What does that 84 inches mean in the context of this problem?
Amount of sand left in the time.
I think you're on the right track, but let's keep exploring that. Good. Okay. I want to talk about that for a moment here. You see how that integral of h prime, I want us to just kind of I want us to connect this with first theorem. So first theorem, imagine you were just trying to do what we were doing before. We know h prime is going to change, right? So you know that with first theorem, h prime is going to change, and then we plug in the upper and lower bound. So this process is just going to be basically h prime rising up to h of t, and then we plug in our upper and lower bound, h of 12 minus h of 0. That is what that 84 inches is telling us. And that's exactly right, right? H of 12, so let's break this down. H of 12 is what? What is this? What does that H of 12 mean? Okay, the height of the sand pile. Okay, good. Height of the sand pile at 12 minutes, whatever that value is. H of 0 is the initial height, right? So H of 12 minus H of 0 is, like what Jesse said, is the change in height between the 0 and 12th minute. Okay, so 84 inches is the change in height of the sand pit in this 12-minute period. I think the natural tendency is we see the 84 inches and we just want to say, okay, that just means the height of the sand pit, right? But that's not necessarily true, because H of 0, the sand pile may already be a certain height, but then it's going to rise 84 inches between 0 and 12. So that's like the subtle thing that we need to be able to understand. Is the change in height, not the height itself. Okay, any questions there? No.
Have you ever asked, like what we have here, like, given this right endpoint, this final height or whatever, to find the initial and then you go through this process?
Right, so if the problem says, what is the height of the sand pile at 12 minutes, then we'll have to take this and add it to the initial to get the final, right? But that's different than just this part right here. So yeah, so if it's saying, what is the height of the sand pile at 12 minutes, then we will have to know what H of 0 is and then add it onto that 84. All right. Tomorrow afternoon, I'm going to try to finish up the rest of this this worksheet here, hopefully you guys can make progress with this. The key is not up yet. I'll make sure I have that key ready this afternoon so you guys can make progress with it, but I'll record the help session so you guys can see the rest of this worksheet being worked out. And tomorrow again is when your assignment is due. Assignments 5 through 7. And then Wednesday, we'll do worksheet 3. And then Thursday is your quiz. Okay, but we're just going to keep revisiting, kind of circling these topics. Yeah, doing variations of worksheet 1. Okay. All right. Thanks, everyone. Hope you guys have a great day. I'll see you guys Wednesday.